Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum, dear students. Today we are going to learn about the permeability and seepage. In our today's lecture, we are going to study first about the permeability of the soils, the scope of the permeability in geotechnical engineering will be studied afterwards. Then we will study about the Darcy's law, hydraulic conductivity of the soil, that how we can find out using the lab experiments. There are two methods. One is the constant head permeability test, and the second one is the falling or variable head permeability test. Seepage Laplace equation for two-dimensional flow nets and problem related to the flow nets uplift pressure due to seepage, or the problem number 4, will be discussed in our next video. So starting with the permeability. What is permeability? Permeability is the measure of the soil's ability to permit water to flow through its pores or voids. And you already know about the soil. In the phase relationships, we already know and discussed that there are voids present in a soil. Therefore, if the water particles are flowing through these pores, it will be dependent upon the pores or voids which are present in that particular soil. So it's a property of a soil. Now, soils are permeable due to the existence of interconnected voids through which water can flow from points of high energy to the points of low energy. For example, if we are having a point here, that point A is at higher energy than the point B, and if we make a tank here, we provide a connection, water particles will flow from this point to this point because that point A is at higher energy. If we take datum, a reference point or line here. Now, particle sizes and the structural arrangement of the size of these particles influence the rate of flow in soil. Particle sizes and structural arrangement is important. Let us take an example that, for example, we are having rounded shaped particles present in a soil, and we are having a loose fabric of that soil. So we are having higher voids or more voids are present in that particular soil. Therefore, the water particles are easy to flow and it will give us the high permeability. Similarly, if the same soil is compacted and densified, now we are having lesser voids and the water particles will be difficult to flow and it will give us the low permeability. Now, a soil is highly pervious when water can flow through it easily. For example, in sand, gravel or gravel sand mixtures, those particles are highly pervious. In an impervious soil, the permeability is very low and water can easily flow through it. For example, if you are taking silts, clays and silt clay mixtures, these are considered to be the impervious soils. Rocks are also considered as impermeable. Now, the scope of permeability in geotechnical engineering. Stability analysis of foundations and foundation excavations are coming in contact with flowing water and underground and our groundwater. In our introductory lecture, we showed you few videos, few famous geotechnical failures of foundations and foundation excavations, where the increase in the hydrostatic forces or the seepage forces failed various retaining structures and in the excavations as well. Stability analysis of seepage through dams and embankments are also conducted. Therefore, the concepts of seepage and permeability is important in understanding the permeability or seepage behavior of the particular soil which are used in dams and embankments. Stability analysis of seepage through earth retaining walls, design of drainage systems, water lowering and estimation of well yields and design of tube wells. The knowledge, understanding of these concepts are absolutely vital in the designing of these geotechnical structures. Now, what causes the water to flow? Now, the total head causing a water flow is given by the Bernoulli's equation, and based upon that equation, the total head is equal to the pressure head, which is occurring due to the pressure, pore water pressure, the velocity of water particles and the elevation from where that flow is occurring. So pressure head, velocity head and elevation head will give us the total head. Let us take an example that we are having an element of a soil and we dig a hole in it and we place standpipe at point A. We dig another hole and we place another standpipe at point B. Now the water is flowing from left side and the water will raise till this point. Let's call that as H1. And the water will also flow here from point A till point B, and the water level or the piezometric level, this point will be H2, and you can see the difference in the H1 and H2. That is known as head loss, or in simple wording we can call that as the energy losses which have occurred from point A till point B. That is head loss. Now ZA is the elevation head at point A. ZB is the elevation head at point B. UB divided by gamma W are the unit weight of water, that is the pressure head at point B, and UA divided by gamma W, that is the pressure head at point A. This is the datum. U is the pore water pressure and V is the velocity, and you can find out the unit weight by multiplying the density into the acceleration due to gravity. Now we discussed about the Bernoulli's equation, and to find out the total head, which is dependent upon the pressure head, velocity head and the elevation head. But in case of water flowing through soil, velocity head can be neglected because the seepage velocity is small. Hence we can say that the piezometric head will be equal to the pressure head plus the elevation head. These are very important equations which can be used in solving various problems or numericals in assignments, quizzes and during the exams as well. So we can also write the head loss by subtracting the head at point A and head at point B by using these equations in such a form. Now the head loss can be expressed in a non-dimensional form. For example, I, and that is the hydraulic gradient. What is L? L is the distance between points A and B, that is the length of flow over which the loss of head occurred. In this case, L is from this point till this point, A and point B. Or we can also define the hydraulic gradient between A and B is the total head loss per unit length. We can represent that using this equation. Now Darcy's laws provides an equation for finding flow of fluid through porous medium. Now according to Darcy, he stated that the flow rate per unit area is directly proportional to the hydraulic gradient, or we can also write in this form that the velocity is directly proportional to the hydraulic gradient, or the flow rate is directly proportional to the hydraulic gradient, and we can write that in this form, that Q is equal to KAI. Now that Darcy law is valid for laminar flow conditions, and that constant of proportionality K is the coefficient of permeability of soil, which can be measured in centimeter per second. Now Darcy velocity is a fictitious velocity since it assumes that flow occurs through the entire cross section of the soil sample. But we know that flow actually takes place only through the interconnected pore channels. Discharge velocity is less than seepage velocity. Let's take that the flow is occurring from the left side, from this point till this point. If we take the cross-sectional area, this is the total area of that soil element. That area can be divided into the area of voids and area of solids. Actually, the flow is occurring through these voids. Now let us take another example, that we are having a tank A and tank B, and if we pour water into that tank, the flow will occur, and this is the soil element which we placed in this pipe. Again the flow will occur and it will come to this tank B. That flow is occurring due to the head at tank A and there is head at tank B. Delta H will become 0 when the level of water here and here will equal, or the head 1 is equal to head 2, then delta H will be equal to 0, or the head loss will be equal to 0. Now we can clearly see that if we take a cross-sectional area from at this point, at this point and at this point, we can see that the cross-sectional area is changing at these three particular points. Now Q is constant and the area, cross-sectional area, is changing. Now in order to keep the flow rate constant, the velocity must change. This states that the seepage velocity in here will be different than the discharge velocity at this particular point, or at point A, B and C. So discharge velocity at point A and point B will be different. Now mathematically we can also prove that the flow rate is equal to the discharge velocity. Now that V is the discharge velocity, and Vs we can call that as seepage velocity. A sub V is the area of void in the cross section of the specimen, and we already know that the total area, we can divide that in area of voids and area of solids. Now we can put, we call that as equation 1, and this is the equation 2, and if you put the equation number 2 in the equation number 1, we can write that the flow rate is equal to the discharge velocity into the total area, or area of voids into the seepage velocity. Area of voids and seepage velocity is on the right side, but we can here discharge velocity into area of voids plus area of solids. Now we can rearrange for the seepage velocity, because we are finding a relationship between the seepage and the discharge velocity. We will multiply and divide that with the length of that specimen which we placed in that pipe. We will get the relation in terms of volumes of voids and volume of solids. Now we can simply divide the numerator and denominator by the volume of solids, and we already know that volume of voids to the volume of solids is equal to the void ratio. So we'll come up with a relationship that V is equal to N into Vs, where N is the porosity, V is the discharge velocity, and Vs is the seepage velocity. So mathematically it's also been proved that discharge velocity is less than the seepage velocity, because the porosity is always less than the 100%. Now there are certain assumptions which are made in Darcy's law. The soil is saturated, the flow is laminar, the flow is continuous and steady, total cross-sectional area of the soil mass is considered. Now in fine-grained soils, voids are very small and flow is necessarily laminar. However, in fractured rocks, stones, gravels and very coarse sands, turbulent flow conditions may exist. Now, how we can find out the hydraulic conductivity? There is a famous relationship where we can write that K is equal to small qL divided by AH, and that Q is the flow rate and that Q is the volume of water per unit. Okay, you can write that T is equal to time, or the flow rate is Q divided by T. So simply they have replaced that small q by T, and you can find out the K, which is the coefficient of permeability, which will be discussed in determining the coefficient of permeability using the constant head permeability test and the falling head permeability test. So Q is the discharge, and that capital Q is the total volume of water, T is the time period, H is the head causing the flow, L is the length of the manometer outlets, A is the cross-sectional area of the specimen. Now, what are the factors affecting the hydraulic conductivity? So there are several factors which affect the hydraulic conductivity or the coefficient of permeability. First one is the porosity of void ratio, porosity or ratio of the soil. Second one is the grain size, shape and distribution will also affect the permeability of the soil. The degree of saturation, viscosity of the soil. So these are few parameters or factors which affect the hydraulic conductivity. Now, for a fairly uniform sand, or we can call that as sand having small uniformity coefficient, Hazen in 1930 proposed an empirical relationship for hydraulic conductivity, where he proposed a relationship with the effective size or D10, that coefficient of permeability in centimeter per second is equal to C square of 10, or the effective size. C is a constant that varies from 1 to 1.5. But this equation is only valid for loose soil. Clean sand, coefficient of uniformity less than 2, and the particle sizes, or the D10, is in this range. There are typical values of hydraulic conductivity of saturated soils. For example, for clean gravel, it will range 1 to 100 centimeter per second. For fine sand, it will be in between 0.001 till 0.01. For clays, you can clearly see that the coefficient of permeability in centimeter per second is less than 0.00001. Now, the coefficient of permeability or the hydraulic conductivity of a layer may vary with direction of flow. One thing is clear, that the horizontal coefficient of permeability and the vertical coefficient of permeability will be different. Now, stratified soil deposits large variation in Kv and Kh from layers to layers. Thus, equivalent hydraulic conductivity is calculated for layered soil deposits. Please kindly note down these two equations, they are very important. Now, Kh is the equivalent hydraulic conductivity for the flow which is occurring in the horizontal direction, and Kv equivalent is the flow in the hydraulic conductivity, and what the equivalent hydraulic conductivity when the flow is occurring in vertical direction. That H is the thickness of those all layers. Kh1 is the hydraulic conductivity for the first layer, H1 is the thickness of the first layer, and so on, the hydraulic conductivity for the second layer and the thickness of the second layer, and if n number of layers are there, so you can use this equation. If the flow is occurring in vertical direction, that H is the thickness of all the layers. H1, H2, H3 are the thickness of the respective layers which are present in the field. Kv1 is the hydraulic conductivity for the first layer, second, third and nth layer. If the flow is occurring in the horizontal direction, that's how we can find out the vertical hydraulic conductivity on the horizontal hydraulic conductivity for the layers thickness H1, H2, H3 and nth layer. Similarly, if the flow is occurring in the vertical direction, We can also find out the KH2 or KV1, KV2, KV3 if we place standpipes at the particular levels. Now, one thing which we need to understand, for example, in the horizontal direction, if we are having a clay layer, or we can say there are 3 clay layers and 1 sand layer, 4 clay layers and 1 sand layer, and we are having sand layer, sand layer, sand layer, clay layer and sand layer. In the horizontal direction, or the flow, when the flow is occurring in the horizontal direction, the soil layer having the greater coefficient of permeability will dominate, or the equivalent KH equivalent will be dependent upon a soil layer having the highest coefficient of permeability. However, in case of the vertical flow, KV equivalent will be dependent upon that layer which is having the smallest coefficient of permeability, because the coefficient of permeability of that clay layer is very small. However, in the case of KH equivalent, the flow will occur through this highly permeable soil layer. Therefore, the KH value will be greater than the KH equivalent value will be greater than the KV equivalent. Now, the coefficient of permeability is determined in the laboratory using 2 methods: constant head permeability test for coarse-grained soils, sands and gravels and their mixtures, falling head permeability test for fine-grained soils, silts and their mixtures. These 2 methods will be discussed in our coming video. Thank you for watching those videos, and thank you for subscribing to my YouTube channel. If you haven't subscribed, please kindly like, share and subscribe to my YouTube channel. Thank you very much. Assalamu alaikum and Allah Hafiz.